And so then it's my pleasure to introduce Chris Hoynen for the fourth and final lecture. It will be on sheaves and the sheaf representation theorem, I think. Chris, your turn.
That's completely correct. Thank you, Jörg. So today we'll be talking about the thing we've been building up to the whole time, namely, you give me a monoidal category, I will represent it as a sort of continuously varying smaller monoidal categories. But to do that, I have to talk a bit about sheaves first. So many people might know this already. If so, apologies. You can go to sleep for a bit, or you can try and learn something new. So the idea is this. A sheaf is a continuously parametrized object, just in general. When I say continuously, I mean there's some base topological space, and this object sort of varies as the point in the space varies. And when I say object, I really mean any object at all. Typically, we'll talk about set-valued sheaves, or many people talk about ring-valued sheaves, where each of the little things is a ring. But you could equally well talk about where each of the little things is a category, or even a monoidal category, as we will be doing. So that's part one. Part two is, if you start with any monoidal category C that has universal joins, then there is this built-in base space of its central idempotence already. So I'll be using that as a base space. And over that base space, we'll define small categories, or smaller ones. Namely, if you have an open in the base space, we'll define C restrict to U, sort of the local sections, if you like. And if you have a point in the base space, we'll define something called C over X, C restrict X, which is it's called the stalk, and it's like a tiny category. And these are the things that will vary continuously, the tiny ones. And to say that they vary continuously, we need to talk about the small ones over opens. So eventually what we'd like to say is that C, the big monoidal category, is a sheaf of the CX's, the tiny ones, where the point ranges continuously over this base space of central idempotence. And moreover, all the tiny ones, I will prove that they're tiny in the sense that they are local, as we talked about. So there, if you take one of the tiny categories, their central idempotence will be a lot like a singleton space, right? You can't make them any tinier in that sense. So that's the plan for today. I hope that makes sense. But first, I'll have to talk a bit about point one, about what is a sheaf in the first place. And to talk about what is a sheaf, I first have to talk about what is a pre-sheaf, because mathematicians have this great habit of, they want to talk about something, and then they first talk about hemi, demi, semi, pre things. And eventually you peel away all the stuff that doesn't matter. So a pre-sheaf on a topological space is just a functor that takes an open subset of the space and attaches some sort of set over to it, in such a way that if you go to a larger open subset of the base space, there's a map from the set attached to the large one to a set attached to the small one. Right? That's all it is. You attach some set of data to an open subset in a way that when the subset grows, the data shrinks in a sense. And the example to keep in mind is, I made a picture here, maybe we should talk about that. It's a very sort of pedagogically incorrect picture in that the x-axis is literally labeled with x, the topological base space, but the y-axis is labeled set. So if you take an open in the base space U there, you will see the set f of u sort of living over it, if you like. And if you have a bigger v, there's a set f of v living over that. And because u is contained in v, we insist that there is a function from the big blue rectangle to the small blue one. And we'll call that restriction. And the sets that are attached to open, so these fu and these fv, we'll call those sets of local sections. We'll call elements of them local sections over u and v respectively. Because the following is the classic example that you should keep in mind. I'm going to describe a pre-sheaf on a base space X. Which set of data does it attach to an open U? Well, it takes a set of all continuous functions from U to the real numbers. Right, so the data attached to an open is all functions, all functionals on it, if you like. And then what does the restriction map? What does the pre-sheaf do on morphisms? If U is contained in a larger open V, then I have to find a way to turn a continuous function from V to R into a function from U to R. But I can't just do that, right? Because U is smaller than V, I can just restrict that function, that local section, to to be a function on the smaller open set. Right, so that is a pre-sheaf, just some way to attach to opens data sets, if you like, in a way that is globally compatible. Now, a sheaf is the thing we're really interested in, is a pre-sheaf that is continuous. And by continuous, I really mean in the categorical sense of preserving limits. So if you look at this, the first line of equations here, on the left we have the value of the sheaf f on the join of a bunch of opens ui. So the join is a co-limit, is a co-limit in OX, which means it's a limit in OX op, right? Because the pre-sheaf was a contravariant thing, it went out of OX op. So this is the f of a limit. On the other side, we want that to be equal to the limit of the f's. And the f of ui are the data we attach to the opens ui, so they're just sets, and we know how to take limits of sets. Specifically, we know you can compute them as an equalizer of a product. So I can just compute what the limit of the fui is, namely it's the family of local sections, one over each open that we're talking about, that are pairwise compatible in the sense that if I take two opens, ui and uj, then their intersection is going to be smaller than ui and it's going to be smaller than uj. So if I have a local section over ui, I can restrict it to an open section, local section over the intersection. And similarly, if I have a local section over uj, I can restrict it to a local section over the intersection. I want these two local sections to be the same. So if you read this formula, what it's saying, the left-hand side says that global sections are family of local sections that are pairwise compatible. There should be a bijection, a natural bijection between these things. Both injective and surjective means something here. So the way you can think about this is in the picture as down there. Again, on the x-axis we have the space x, on the y-axis we have set. Again, we have two opens u and v. There's some set fu living over u, and there's some set fv living over v. But now I've also drawn in two local sections. So there's an element of fu, that is I think the color is called teal maybe, or turquoise, on the left. And there's an element of fv that sort of lives in pink on the right. And the fact that these two sections are pairwise compatible means that when I restrict to f of u intersect v, like the set that lives over the intersection of u and v, there the two local sections are literally the same. So if this is the case, then I want there to be a single global section on the left-hand side. So I want there to be an element of f of the union now of u and v that restricts to the two things I chose, the pink one and the teal one. Right, so you should think about this as I can glue together compatible local sections into unique global section. If I have a cover ui of some big open u, and I have local sections over each of the parts of the cover that do the right thing in the overlap, then I can paste them all together into a big section over all of u. Right, that's the definition of a sheaf. So sheaf is a continuous pre-sheaf. Now I need to go a bit further because we've only talked about opens so far, and I want to talk about points at the end of the day, points of the base space. So what a sheaf did, it assigned to opens of the base space data. What about if I have a point of the base space? So if you give me a sheaf and a point, I can talk about its stock. I can look at all the open neighborhoods of that point. They will all have fu sets of data attached to them that get smaller and smaller and smaller and smaller, if you like. And I want to take their co-limit. So I take the point, look at all the smaller and smaller neighbors of the point. They come with smaller and smaller sets over them. I take the co-limit of those sets. And again, because we're in sets, we know exactly how to compute this co-limit. It's just a quotient of a co-product. So we can say that the elements of such a stock, they're called germs typically. And they look like this. It's a co-product. They're represented by a local section over some open neighborhood u of the point. But I'm going to identify two such local sections when the following happens. So let's say one representative f that lives over a neighborhood u of the point, another representative g that lives over a neighborhood v of the point. I'm going to say they are equal. They're going to be identified. exactly when I go to the intersection, they do the same thing. So in the gray thought bubble on the bottom right there, two local sections are considered the same when they do the same thing in a small neighborhood of X. I don't really care how small. If you can go smaller and smaller, if at some point they become equal, then they're equal for all intents and purposes. So I'm really only interested in the germs of functions, sort of how they behave around the point, the immediate neighborhood of the point. So if I try to picture this in the non-pedagogical way as in the bottom left here, with z on the y-axis and x on the x-axis, a germ over the point x can be represented by various local sections in black there, and they're all identified as long as they just above x in a tiny, tiny neighborhood, they do the same thing. So these two local sections there will give the same germ. All right, so so just to recap, a sheaf is a continuous pre-sheaf. It says something about open sets and the data above it and how to paste together elements of these sets. And a stalk is what happens if you look at a single point. So they're like tiny, tiny things of the continuously varying set. I hope that makes some sense. Now, for one example, one way this is typically used is in what's called a Serre-Swan type of theorem. Specifically, earlier we talked about Hilbert modules, A, and there's a theorem for these things due to Takahashi that says to give a Hilbert module over C naught x, where x is some base space, is the exact same thing as giving a continuous field of Hilbert spaces over x. So that means in the picture down there, I have a base space x. Over each point of x, I attach a Hilbert space, not just a set, but a Hilbert space. And I want this Hilbert space to vary continuously. So that means if x varies a tiny bit, then the Hilbert space varies a tiny bit. Now, of course, you're going to ask, what does it mean for the Hilbert space to vary a tiny bit? So by that, I mean all these fibers, these two Hilbert spaces that are close together, are part of the larger topological space E over there. So it makes sense that, you know, points in EX and points in EY are close to each other. But also, I want the operations, the algebraic operations of the Hilbert space to vary continuously. So things like scalar multiplication and vector addition and inner product, I want them to vary continuously as x varies a little bit. So that you can say as if you have this bundle of a total space E with a continuous surjection down onto the set X that we're interested in, and each fiber EX is a Hilbert space, that means that each fiber comes with a inner product. But you can also look at the pullback of E with itself over X, and that will also have some sort of inner product. I want that to be continuous. In that sense, the inner product varies continuously as you vary the base point. And the idea of this theorem is, I was talking about continuous fields of Hilbert spaces, which is literally what's defined down there. That turns out to be the same thing as a sheaf of Hilbert spaces over X, or if you know about topos theory, a Hilbert space defined internally in the topos of sheaves over X. And how you go up and down between a Hilbert module and such a sheaf of Hilbert spaces or a continuous field of Hilbert spaces is quite typical. Namely, if you take a continuous field of Hilbert spaces, how do I make a module? I look at all the local sections, all the global sections, and going down, if you give me a module, how do I make it into a field? What are the stalks? You can do something called localization. So you identify all elements of the module when they do the same thing on X, above the point X, if you like. So this is one example that we looked at before, where this sort of sheaf theory plays a real role. Now, so far we've talked about sheaves of sets, and I've been a bit vague in the last slide about sheaves of Hilbert spaces. And we said a sheaf of sets is a continuous pre-sheaf on X that takes values in the category set. You can do the exact same thing for rings, for example. So a sheaf of rings is just a pre-sheaf that takes values in the category of rings and ring homomorphisms. And you can do the same thing for categories or monoidal categories, or stiff categories. So what we're going to be interested in is sheaves of monoidal categories. So a sheaf of monoidal categories is a pre-sheaf on some topological base space X that takes values not in set, but in monoidal categories, stiff monoidal categories and their functors. Now, I said before that the sheaf condition over here says that a sheaf is a continuous pre-sheaf, so it should preserve limits, right? And because we were in set before, I knew how to compute this limit, and that's how we got to the description in terms of pasting local sections together. But if we take values in monoidal categories, I in principle don't really know what this limit looks like. So the best I can say, I can just describe what this limit looks like. And I'm going to define a sheaf of stiff categories to be a pre-sheaf such that the following thing here in the middle is an equalizer. So this is really the same thing we were doing before when we got to the description of local sections being pasted together. But now I've just left it in the abstract. I haven't computed what actual elements of these things are because they're no longer sets, they don't have elements. So the thing on the left is the value of the sheaf f at the join of a bunch of opens ui. So we can think of those as the global sections, if you like. I want that to be an equalizer of the two parallel morphisms on the right. The domain of those two parallel morphisms are the products of the values that the sheaf attaches to each of the opens. So you can think of those as families of local sections, if you will. The thing on the right is families of things over the intersections of a bunch of two of these opens that we're interested in, and the value that f attaches to them. And the two arrows say that the families over U of local sections over UI that we're talking about should be pairwise compatible. They're literally encoding what we were saying before, that if you have UI and UJ and you have two local sections, then they should do the same thing on the intersection of UI and UJ. And we're just going to take this as a definition. So a sheaf of stiff categories is a functor from OX up to moncat S that makes the following thing into an equalizer in moncat S. So this whole diagram consists of monoidal categories, and the arrows on it are monoidal functors. I want that to be an equalizer. And we're going to say f is a sheaf of something something, exactly when its stalks do something something. So for example, we had a sheaf of sets before, just means that the stalks are sets, pure and simple. But we can talk about a sheaf of local rings, for example. That means that the functor f takes values in the category ring, but additionally all the stalks are not just rings, excuse me, not just rings, but local rings, whatever that may mean. And specifically, we're going to be interested in local categories. So I'm going to say that f is a sheaf of local monoidal categories. That means it's a sheaf on a base space that takes values in monoidal categories, but all of the stalks are going to be local categories, right? And that's going to be one half of the theorem. We're going to show that something is always a sheaf of local monoidal categories. And this is what I mean.
I have forgotten what a local category is, Chris, to be honest.
Sorry, could you repeat that?
I have forgotten what a local category is.
That's a good point. Thanks for reminding me. I think we talked about that here somewhere. So last time we said that a locale is called local if it's sort of tiny in the sense that it looks a lot like a singleton set. Specifically this property here, that if a join of opens is everything, then one of the opens must already be everything. And for topological space, that meant there's a sort of one focal point that determines the whole topology. Now a category is local exactly when its locale of central idempotence is local. So when its base space is sort of as small as it can get. Oops. Does that make sense?
So it is not saying that we have no idempotence whatsoever. This is not what is being said.
In some sense, and in some settings that's going to be true. It's not going to be always true because there will always be at least one trivial.
Right. Except for that. Yes, except for that one. Yeah.
Yes, but except for that, that will be an example of a local category, but you also have ones where, as we saw last time, for example, the natural numbers where the point 0 is a focal point, but there's still lots of other points. But in a sense, they're indistinguishable.
Oh yeah.
So these are sort of the smallest things you can decompose a monoidal category in.
I think I have it.
So our goal is going to be, you give me a green monodal category U with universal joins. I'm going to define the small versions of the local sections, if you like. They have to be stiff monodal categories again. I'm going to prove that they form a sheaf of monodal categories over the central idempotence. And that defines a sheaf. And once we have a sheaf, we just compute the stalks. I will actually, define the stalks and show that they have the right property of, going smaller and smaller. And we're going to prove that they are local, right? Because that's what it means for a sheaf to be a sheaf of local monoidal categories. And we're going to look a bit at the relationships and properties that if C has something, what can you tell about the local sections and about the stalks? That's the goal for today. All right, there we go. So you give me a monoidal category C that has universal joins. I pick one universal join, U, and we fix it for the rest of this slide. And we're going to define sort of the small category of C that only lives over U, C restrict U. The quick way of doing this is by saying that the functor blank tensor U is an endofunctor on C. Right? It takes an object A to an object A tensor U. But it's not just that, because U is idempotent, is even a co-monad on C, and I can look at its co-Kleisli category. But that's only for people that know this kind of thing. Maybe it's easier to just spell out what this category looks like. So the objects of the new category are going to be the same ones as in the old one. So all the C restrict U will have the exact same objects, namely the same ones as C, but the morphisms are going to be different. A morphism from A to B in C restrict U is the same thing as a morphism in the old category C, in the big category C, but not from A to B, but from A tensor U to B. So what this A tensor U to B is doing is a sort of cutting down this morphism to make sure it only lives over U, if you like. So those will choose to be the morphisms. How do we compose two such morphisms? Well, so you give me an F that goes from AU to B and a G that goes from BU to C. I start at AU and have to end up at C. So what do? I copy the U, which I can do because it's a central idempotent. I use one copy to feed into the F, and then I use a second copy to feed into the G. And that's how I define composition. You can prove that this is associative, and you can prove that it has identities, namely, what's the identity on the object A? So that has to be a morphism from A times U to A in the big category C. And what do? I keep A as it is, and I just forget about the U. So it's A tensor little u, if you like. You can prove this is a well-defined category, and this is what I define to be the categories of local section, C restrict U. It's not just a category, it's in fact a monoidal category again. Let me tell you how. The tensor product of two maps. So first of all, the tensor product of two objects is going to be the same as the tensor product as it was in C, in the big category. The tensor product of two morphisms, F and G. So they are both maps from A times U to B and from A prime times U to B prime, let's say. We have to produce a map from A times A prime times U to B times B prime. And what I do, I copy the U, so I can use it in both F and G, and I have to sort of swap around the middle two things to make things match, but I can do that because U is central, comes with a half braiding. I can swap it with arbitrary objects. The associator, so that means I have to find a map from A tensor bracket B tensor C, whole thing tensor U, to, with the brackets the other way around, A tensor B bracketed tensor C. And again, you don't really see it in this graphical notation, but there is an associator of the big category C involved here. But basically what you do is you leave the A, B, C intact and you just forget about the U. So in other words, you just take the associator from downstairs and sort of import it by force into C restrict U. And same kind of thing for the uniters. So if I want to define what the uniter in the small category C restrict U is, I have to find a map from I times A times U to A. I first use the uniter of C to get rid of the I, and then I use the central idempotent U itself to get rid of the U. And you can do the same thing for the right uniter, where you go from A times I times U to A. Forget about the I with the right uniter from downstairs, forget about the U, just using the fact that U is a central idempotent. And in the good tradition of thinking for yourself, and math is not a spectator sport, now maybe you can have a think about for a minute, for example, why this might satisfy the, let's say, the triangle equality. So
I have a question before that, Chris. Why,
yeah, sure.
why is the right uniter not defined in the other order, so to speak? In the so it should be. I would have there. You cannot see my screen, but in the right uniter, I would have AUI instead of AIU.
Okay, let's go back to the definition. So a morphism, the right uniter is a map from A times I to A, you could be right in that. But a morphism in CU from A to B,
right,
is something that goes, so you always just attach the U to the right of the domain you're really interested in.
Oh yeah, you're right. Yes, that's correct. You are
So
right.
that goes AIU.
Yeah, I agree. Mm-hmm.
But in practice, it doesn't really matter, I guess.
That is true. It doesn't, because you are central, but I got the order wrong and you got it right. Let's be very clear about it. Mm-hmm.
I'm hoping that today finally will not have a single typo. I try to take care.
What are we supposed to do?
You're supposed to think about this so you get a bit of a feel for how this model category works. Think you have a feel? Let's just say you do. Right, so given a central idempotent U, we've defined this small category of local sections, and it's not just a category, it's monoidal. Now, just as an intermezzo, if the category we started with had not just tensor products, but actual Cartesian products, then this thing we have defined, this small category C restrict U, is in fact equivalent to the slice category C over U that we talked about at the very beginning. So the objects here are maps into U, and the morphisms are commuting triangles. And that's kind of interesting to see. So I'll try and walk you through this proof. So first, in this small category C restrict U, I claim that any object A is isomorphic to itself tensor U. And you can see that by literally just writing down the two maps that implement the isomorphism, that are the inverses. So to go from A to A tensor U in C restrict U is the same as going from A times U to A times U in the big category C. And then we can just use the identity that is such a map. Go the other way in the small category, from A times U to A in the small category is the same as going from A times U to A in the big category. And we can also build a map like that just plain forgets both of the copies of U. And if you work out what the composition in the small category is, and what the identity in the small category is, you'll find that both compositions, both ways around, are equal to the identity. So in the small categories, it doesn't matter if you tensor with U, you will stay isomorphic to where you started. So that means that C restrict U, the small category, is equivalent to the full subcategory of the big category C, where I only consider the objects of the form A tensor U. Okay, so now I'll compare that category of this full subcategory of all the objects AU with the slice category C over U. So on the left, if you give me an object of the form A tensor U, I'm going to map it to the right by just sort of projecting from A times U to U, which I can do because the tensor product is an actual product. I have projections. To a morphism, I will do the thing that's written down there. I just copy the U, which I can always do. And to go the other way, if I have a map from A to U, and it's sort of fixed which one that is because we're talking about projections, but because we're talking about Cartesian products. I'm just going to map it to A tensor U, and the same for morphisms. And if you calculate going left and then back, or the other way, going first right and then back left, both of them will be isomorphisms. So in other words, if the big category you start with is Cartesian, then the small categories that we defined are slice categories. But the small categories you've defined work in any case, right? Even if C is not Cartesian but just monoidal, there will still be fine monoidal categories. So let's look at some examples. If your big category is set squared, for example, then we saw that the central idempotents, there's 4 of them, and they form this the diamond lattice, if you like. Namely, in each factor of set, you can have 2 central idempotents, namely the singleton set or the empty set, and then you can combine them, as a 4-element Boolean algebra like that. So, for example, one central idempotent I could look at is I take the empty set in the left copy of set, and I take the singleton set in the other copy, in the other factor. Then, what does the category of local sections, this C restrict U, look like? Well, it's literally just equivalent to set, right? In the sort of sense that we're seeing here, it's a full subcategory of set squared, where all the first elements of the pairs are empty sets. So all things of the form empty set, comma, some other set. If the big category you started with is sheaves over some base space, that we now know actually what it means, then you can prove that the central idempotents of the things are the subterminal objects and hence the opens of the base space. So if you fix one such central idempotent, that means fixing one open subset U of the base space, what is C restrict U? Well, it turns out to be exactly sheaves over U. So restricting sheaves over X to U is just sheaves over U. For a third example, if you start with a semi-lattice L and regard it as a monoidal category, we saw that every element, every object of this category whatsoever is a central idempotent in a unique way. So if you fix one central idempotent U, just one element of the lattice, what is the restricted small category? It's exactly the downset of U. So the semi-lattice formed by all elements below U. For a fourth example, if you look at a bialgebra over field and look at modules over this bialgebra, this is a monoidal category where we take the tensor product over A, so not over the base field, but over A. And if you do that, then the central idempotents turn out to be the central idempotents of the bialgebra A. So if you fix one such central idempotent, let's call it E, then what is the restricted category C restrict U? And it turns out to be exactly modules not over A, but over E times A, like the corner of A, E, A, E. And the last example on this slide, if you start with a big category of Hilbert spaces over C naught X, then we saw that the central idempotents are all open subsets of X. If you fix one open subset U, what is the restricted category C restrict U? It's almost Hilbert spaces over C naught U, but not quite, because there's a slight problem here. If you want to go from, so C naught X consists of continuous functions on X that vanish at infinity. C naught U consists of functions over U that vanish at infinity. So if I have a function over C naught U that vanishes at infinity, I can just extend it by zeros. I have a function on C naught X that vanishes at infinity, and that's fine. So I can turn a C naught X module into a C naught U module, that's fine. But these Hilbert modules also have an inner product, and there I need to go the other way. So I need to turn a value in C naught X into a value on C naught U, and that's not clear how to do that. So in general, the best you can say is that the restricted category is the full subcategory of all Hilbert modules A, all of whose elements, all of whose vectors vanish outside of U. So that's a good bunch of examples, and that should give you some feeling for how this restriction, how these small categories look like. So for various big categories, you get these various small categories. Now I want to go one step further. So we know if you fix one open of the base space U, we can find a small category to live over it. What happens if you have two open subsets of the base, one bigger than the other? So if I enlarge the base open, what happens to the things that live above them? It turns out I can find the functor from the larger of the two to the, sorry, from the small one to the smaller one of the two, literally by restricting to the smaller of the two central idempotents. So specifically, if two central idempotents u and v, and u is below v, I can find a functor from C restrict u to C restrict v that does nothing on objects, because remember, they all have the same objects. But to a map, it sort of precomposes with including u into v, as in that picture. The fact that this is a functor is fairly straightforward, but maybe it helps to get a feeling for things if we walk through it a bit slowly. So if we call this functor g, what is g of the identity, for example? Well, so first of all, what does g do? It literally precomposes with the inclusion of u into v. But the identity in CV is literally defined to be doing nothing on A and forgetting about V, so it's the second step. But by definition, the inclusion of U into V and then forgetting V is the same thing as forgetting about U. And that's by definition the identity in CU. So this functor G preserves identities. In a very similar kind of way, you can see that this functor G preserves composition, for example. If you just write down what the functor G does, you'll find the left picture. If you write down what first doing G to both and then composing does, that's the right picture. And all you have to do is sort of slide this inclusion of U into V through the copying of U respectively V, which is just equal by definition. And in the same kind of way, you can prove that this functor G preserves the tensor product on the nose. So it's even a strict monoidal functor. Right, so if you go from a smaller open, to a small open, there's a monoidal functor going from the small category to the smaller category. And in fact, this is not just a functor, but it's a reflection. If U is below V, then the smaller category CU is a reflective subcategory of the small category CV. So the functor we just talked about is the one going right to left. You can also give a functor going from left to right that now changes the objects. It sends an object A in CU to A tensor U in CV. And then you have to do some fiddling with the morphisms to make things match, but the way it's written down here is a fine monoidal functor. And then if you go from CU to CV and then back, you end up with something isomorphic to what you started with. So this is not just an adjunction, but a reflection. But that's just as an intermezzo. So that's great. So now we have a pre-sheaf of monoidal categories. Right? To each open U, I've attached a monoidal category CU living over it. And if U grows into V, then I have a way of restricting CV back down to CU. I have a pre-sheaf of monoidal categories. Now let's see about what the central idempotents in these small categories are. And the claim is that central idempotents in C restrict U are exactly all the central idempotents in the big category C that live below U. It's just a downset of U itself. And let me just have a look at the time whether we want to do this. I think we might want to skip this. I want to say anything about this. Let me try and do it fairly quickly. So we're interested in what are the central idempotents in CU, that's the top line. I want to compare it to what are the central idempotents in C, that's the second line. So if you write down what it means to be central idempotent in CU, you get the thing on the top right, where there exists an F making those pictures true. And when you write out what it means to be a central idempotent in C of the form Q tensor U to I, then you get the picture in the right middle with there exists some G making that picture true. And now you can just show that these two things are equivalent by saying, if you have an F then that does the top thing, then I can find a G that does the bottom thing. You can just write down what it is. And conversely, if I have a G that does the bottom thing, I can write down an F that satisfies the top thing, as the third line here does. So in other words, when we restrict the big category C to a small category CU, what happens to the central idempotents? Well, we take the big set of central idempotents and just look at its downset all the things below U. We sort of cut it down at U. As a corollary of this, now we know exactly what the central idempotents in CU are. You can prove that if the big category was stiff or has finite universal joins or has universal joins, then so does the small one. You can just translate all the properties of central idempotents in the small one back into properties of the central idempotents of the big one. So not only have we got a presheaf of monodal categories, the C restrict U is a presheaf of stiff monodal categories, for example, or monodal categories with universal joins. That's good, we're on our way. Now I want to upgrade this, what we now have as a presheaf. I want to prove that it is in fact a sheaf. So just to recap, the presheaf that we're talking about, it acts, the base space is the central idempotents of C. It takes values in monodal categories. It assigns to the open U, to the central idempotent U, this category that we define C restrict U. To prove that this is a sheaf, remember I have to prove this the sheaf condition that said that a certain thing is a limit, that this here diagram is a limit, is an equalizer. If you write that out a bit, that means that a certain diagram is a pullback, which is a bit easier to prove. The blue diagram in the middle has to be a pullback. So if you have two opens U and V, not necessarily one below the other, they have a join, they have a meet. I can look at the small category C restrict U and the small category C restrict V. They will both restrict further to the even smaller category C restrict to the meet of U and V. And going bigger, they're also, U and V are both below U join V. So I have restrictions from C restrict U join V to CU and to CV. And I claim this is a pullback in the category of monoidal categories. So in other words, if you have any other monodal category A, and monodal functors F and G going into C restrict U and C restrict V, then there's a unique monodal functor H going into C restricted to the join. Because all of these C restrict something categories have the same objects, all we really need to care about is what this map H should do to morphisms. So if you take a morphism from A to B in this extra category green A, and then you get this gray diagram on the bottom right. So you can apply H of A. F and G have to do the same thing on objects. We'll just call it H of A. So you can go from HA times U times V to HA times U or to HA times V. And you can go further from there into the join. Now, by virtue of C having universal joins, I know that this square is a push out. So I can look at what F does to the morphism, what G does to the morphism. There has to be a unique map from HA times the join of U and V to HB. And I want to find that to be the action of H on the morphism. That turns out to be functor, and turns out to be the unique one. It has to be this one. So in other words, the blue square is a pullback of monoidal categories. So in other words, the presheaf that we're talking about is an actual sheaf. So what we've done now is we've taken a big monoidal category C, we've turned it into a sheaf of stiff monoidal categories. That's good. That's half of what I wanted to do. The other half of what I wanted to do is to prove, say something about the stalks and prove that the stalks are really, really tiny in the sense of being local. So first, let me just define something I will call C restrict X, and in the next slide, we will prove that it is actually the stalk. So these are the tiny categories, if you like. So the objects of C restrict X are again going to be the exact same objects as in C. All the objects are always the same. But now the morphisms are going to be even more restricted. A morphism in C restrict in the stalk is an equivalence class of things, of pairs, namely an open neighborhood of the point that we're looking at. So a central idempotent V that's contained in the completely prime filter X, together with a morphism in C that goes from AV to B. So this is a lot like we were defining germs before. We're only sort of interested in how F acts in a tiny, tiny neighborhood of the point. But if, in other words, two representatives, two sort of local sections, if you like, F and F prime are identified, when they do the same, when they act the same on on some smaller part that contains both v and v prime. Sorry, that's contained in both v and v prime. So this is really mimicking the definition of germ of functions, I guess, local sections of set valued sheaves to monoidal categories. So this is just a definition of morphism. And you can compose two morphisms in the same way as before. If you have a representative f that lives over u and a representative g that lives over v, then that composition is going to be, I'm going to define it to be to live over u intersect v, and on u intersect v, I just do first f and then g. I use the u to feed f, I use the v to feed g. The identity is just going to be the identity that we had before, that's defined everywhere.
I don't get this, Chris. The definition should be the intersection, not. So this would be A tensor U tensor V as the domain of the composition. But we need to have A tensor U meet V as the definition, as the domain. Why is this?
Yes, I think that's right. So in the composition, there has to be a map from A to C in the stalk. I'm choosing it to live, the first component of this pair to be U meet V. So the domain of U meet V as a central idempotent is just U tensor V. And that's how it was defined. So the tensor of two central idempotent is its meet. So then I have to find a map in the big category from A times U times V to C. Does that help?
Yes, it does. Yeah.
So really what we're doing here is we take the definition that we had before of C restrict U, just C, the local sections over some open U. And we sort of made it smaller and smaller, and we say two things are the same when they do the same in a tiny neighborhood of the point. We only added this equivalence relation to it in a sense. And that's exactly what's going to help us prove that this thing I've defined is a well-defined category. It's not just a well-defined category, but actually the stalk of this sheaf. So in other words, I have to prove that Cx is a colimit of the Cu with a U range over all neighborhoods of X. The colimit is to be taken in the category of stiff monoidal categories. Right, so I have to prove that this thing is a colimit. So first of all, I have to find the co-cone. So the diagram is over the top line of blue arrows here. And we know that we have these restriction maps going from the big category C to a small category CV to an even smaller category CU, etc., 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 where all the U are neighborhoods of X. And because we defined X to be with this equivalence relation, there's a quotient map that turns a morphism in CU into a morphism in CX by just saying this thing is defined over U and F is a representative. And this is also, that will also help you show that's a colimit, because if there's any other category D and any other functors Fu that make the diagram commute, there's a unique functor M from the stalk to D, and you know exactly what it must do. Namely, you take a representative F that lives over U, and you just look at what the functor Fu does to it, and that's all. It has to be that one. So in other words, this category you've defined here is a very concrete definition, is the stalk. You can prove that it's even isomorphic to the stalk, not just equivalent. Great, so we have a sheaf of stiff monoidal categories. We know what the stalks are. Now I'm going to try and prove that these stalks are in fact local. So I have to say something about what the central idempotents of the stalk are. And the claim is just as before, the central idempotents of the small categories are just the downsets of that small thing. Same way I can just say concretely here, the central idempotents of the stalk are a quotient of the central idempotent of the big thing, where I identify two things when they become the same when restricted to some U, some neighborhood of the point. So if in some neighborhood of the point they have the same intersection, then they're equal as far as I'm concerned here. And that's the exact same proof we had before, except now we just have to make sure everywhere that this equivalence relation is respected. And you can choose representatives, and it doesn't matter which one you choose. So that's good. We know what we have a sheaf. We know what the stalks are. We know what the central idempotents of the stalks are. As a corollary, you can immediately see that if C is stiff or has finite universal joints or has universal joints, and so do all the stalks. That's good. Let's look at some examples. If you're in set squared, so we have this diamond lattice as central idempotence, a point would be a completely prime filter of this lattice. So let's say it's the purple thing there, the upset, the principal filter actually of 0, 1, as we had before. Then the stalk is literally just set, sort of as we had before. And this is in a sense because the central idempotents are a discrete space here. It's a 2-element discrete topological space. But if you do the same thing continuously, you look at sheaves over X, set valued sheaves, and you look at a point of X, then what is the stalk? That is just set itself. Because that's what the germs do. Another interesting thing is, and this comes back to what Jörg was asking earlier, if you start with a Boolean algebra, you can regard that as a monodal category with the meat being the tensor product. You take a point in its, you take a completely prime filter X, then what is the stalk C restrict X? It turns out not to be very small, but even 2-valued. It's always, the 2-element Boolean algebra with just 0 and 1 in it. As we were saying before, if you start with Hilbert modules over X, you take a point of X, what is the stalk? It's now literally 1 copy of just Hilbert spaces. And in that sense, this Takahashi theorem says something about actual Hilbert spaces varying continuously over the base space X. Then finally, what I wanted to mention here is if you take a bialgebra A over a field and look at modules over A, we know that the central idempotents of this category are central idempotents of A itself. But it's not clear to me what the points are, if you have a clean description of them, what it means to be a completely prime filter of central idempotents of a bialgebra. And specifically, I don't know of a concrete, nice description of what the stalks are. I think in principle, they're not going to look like representation categories of bialgebras anymore. But nevertheless, they are something, and I would like to know what they are. Okay, and the final thing that I promised you is that if the big category has finite universal joins, then the small ones are local or sublocal. Sorry, the tiny ones are local. The stalks are local or sublocal. So that means, I'll remind you that, let's look at the finite version that says a join of 2 central idempotents is 1, means that one of the 2 already had to be 1. But this is quite simple to prove because we have now an explicit description of what the central idempotents in the stalk are. So let's assume that the join of U and W is 1. So that means that U join W is equivalent under this stalk equivalence relation to 1. And by definition, that meant there exists some neighborhood of XV that equals U meet V joins V meet W. But now I know, because X is a completely prime filter, X is a point, that means that either U meet V is an X or V meet W is an X. But by definition of the equivalence relation again, that means that either U is equivalent to 1 or W is equivalent to 1. So all in all, these stalks are actually local or sublocal. And then we arrive at the proof we wanted. So now we've proven the following thing, the representation theorem. Any small monoidal category with finite universal joins is monoidally equivalent to the category of global sections of a sheaf of sublocal monoidal categories. Now that's a mouthful. So what we've done is you start with a small monoidal category of universal finite joins, the big category C. We built out of that a sheaf of monoidal categories CU that has stalks CX, and the stalks are all local or sublocal, the tiny categories. But in fact, you can reconstruct C back out of this sheaf of tiny categories by looking at the global sections, which is in gray up there. That's literally just, if you have a sheaf, a global section, I will define, if I have a category valued sheaf, I will define a global section to be an object of, the total category, the category that is the value of the sheaf at the open, that is the whole space. And if you were talking about set-valued sheaves, then that's the same thing as a natural transformation of the singleton sheaf to the sheaf itself. Because, of course, if you do C restrict to 1, to the top central idempotent, that's just C itself. So not only can you turn C into a sheaf of tiny things, you can reconstruct C from the sheaf. Right, so that's the representation theorem. Hopefully now you can understand all the words. So just for repetition, I'll say it once more. Any small monodal category with universal joins is equivalent to a category of global sections of a sheaf of local ones. And together with, so the uptake of this is if you want to prove something about monodal categories with universal finite joins, one way you can do it is you can just plain assume without loss of generality that the category is tiny, that it's sublocal, and that the property you're trying to prove is continuous in the sense that it respects sheaves. If we combine it with this embedding theorem that we had last time, you can forget about the final universal joins even, and you say that any small stiff monodal category embeds fully into such a category of global sections. So not only if I want to prove something about a monodal category, can I assume that it's tiny, that it's sublocal, I can even assume that it doesn't even need to have universal joins. Stiff is good enough. If I want to prove something about stiff monodal categories, it's good enough to assume that it's tiny. That's the point of this theorem. And I'll remind you, stiff is a property that's very, very weak. So basically, if you want to prove anything about a monodal category, you can assume using this theorem that it's tiny, that it is sublocal. This sort of representation theorem has been done before, and the version I just showed you is very, very general and subsumes some of these earlier versions. Specifically, there's one for toposes, that's due to Lambeek and Moerdijk and Audi. There's one for Hilbert modules that I mentioned earlier due to Takahashi. There's one for modules over commutative rings, that's sometimes called a Pierce spectrum. And one that we just saw is, that we saw here, is if you start with a Boolean algebra, all the tiny things are actually two-valued. So if you work out what the sheaf representation theorem there says, it says that any Boolean algebra is equivalent to a category of global sections of a sheaf of two-valued Boolean algebras. And that's just a fancy way of giving the stone representation theorem for a Boolean algebra. So this is a nice general theorem that captures lots of settings, is the point. You can make it functorial if you like, but I don't like to do that now, in the sense that, so what the representation theorem said is that a monodal category you can turn into a sheaf. If you define the right notion of monodal functors between monodal categories, you also get some sort of notion of morphisms between sheaves, and it becomes an equivalence of categories. Now, the last thing I want to do before summarizing is talk a bit about preservation. If you start with a big category, it's not just monodal, but has some other properties. It turns out that the small categories and the tiny ones very often inherit those properties. So, for example, one thing that we just saw is that if your big category is Boolean, in the sense that its central idempotent is from not just a semilattice, but even a Boolean algebra, then the same is true for the small categories, and the same is true for the stalks. And in fact, the stalks will be extra simple, right? They will be two-valued, not just any Boolean algebra, but a very, very tiny one. If your big category is closed, in the sense that it doesn't allow just tensor products, but in fact exponentials or hum functors, then also the stalks and the tiny and the small categories will have that. And the same if your big category is traced, in the sense that you have what's called a traced monodal category. I've tried to make a picture on the left there. If you know what it is, then you'll know what it is. If you don't, I'm not going to be able to tell you in a minute. But this is a property that's really about monodal categories that doesn't often play a role for Cartesian categories. And the same goes for compactness. So your monodal category could have the property that every object has a dual. So something like, if you think about finite dimensional vector spaces, every object comes with a dual vector space. If your big category has that property of compactness, then so will the small categories and the tiny categories. If your big category has limits of a certain shape J, then so will the local sections, the small categories and the tiny categories. And almost you could say the same about co-limits, but you have to be a bit careful that the co-limits, the shape of the co-limits, the shape of the diagram that you're taking co-limits over respects the tensor product. So lots of properties of the big category are inherited by the tiny categories. So you have 1, 2, 3, 4, 5, 6 other representation theorems on this slide. For example, saying any small, stiff, closed monodal category is equivalent to a category of global sections of a sheaf of closed local monoidal categories. So in that sense, this representation is very well behaved. All right, so now we've come to the end. Let me summarize what we've done today. So we saw that sheaves are continuously parametrized objects. We talked about how you can formalize this. Then we built a sheaf, first of all, by starting with a big category C, taking a single central idempotent and making a small category C restrict U. We computed the stalks and we proved this representation theorem, saying that if the big category have universal finite joins, then it consists of continuously varying tiny categories C restrict X that vary continuously over this base space of central idempotents of the big category. And the upshot of that is that if you want to prove anything about a stiff category, you can just pretend that the thing is local, if that makes your proof easier. This is a representation theorem that subsumes various earlier ones, for example, Stone's theorem. And the nice thing about it is that if I go all the way back to the first lecture, we talked about categories, monodal categories, braided monodal categories, that they have these graphical calculus that's one-dimensional, two-dimensional, three-dimensional. Then in the second lecture, we talked about these central idempotents. They form something like a base space, but it's sort of hidden inside there. It's not like an extra direction in the graphical, extra dimension in the graphical calculus. But what this representation theorem does is sort of cleanly separates the, the spatial and the temporal directions. Spatial now in the sense of central idempotents, temporal in the sense of all the monoidal categories, the tiny monoidal categories. There's more to be said about this, but I think we'll stop there. This is sort of the beginning of a story. And now it's up to you to think more about, there's lots of questions to be solved about this. But I'll stop there. Thank you very much.
Thank you, Chris. So are there questions?
I actually have a quick question, if you don't mind.
Nobody minds.
When you were going through the story, why did you, out of curiosity, why did you expect to get sheaves of monoidal categories instead of more stacks of monoidal categories? Because whenever I've seen in the past a sheaf of category type construction, it's always turned out to be a stack that you need instead. And I'm just wondering sort of what magic goes on that really allowed you to say, contract all those natural isomorphisms.
Yes. So, for example, there's typical representation theorem for sheaf representation theorem for toposes in the OD version, for example, that does go through stacks. And I think the magic that's going on there is this thing here. So the way they define the small categories is you take slices of the big category over the subterminal that's given by that open. And there's some choices to be made there. And I mean, you have products, but you don't have chosen products. So that's why you need to, this is only an equivalence in general.
Yeah.
If we're doing everything based on a monodal category, you have, there's a well-defined object on the nose of A tensor B. It's not that, if you have products, then you say some A times B exists and it's unique up to ISO. But here we have one fixed thing. And I think that's what makes it different. So we can circumvent all this. So Audi has this thing, say, he relies on a lemma saying, what is it again? Any stack of a certain type is a sheaf.
Oh, okay,
You have to use some sort of choice argument in there. I think we sort of pull the choice argument earlier by just defining CU sort of without choice.
Okay, thank you. That's certainly something for me to look at and think about carefully too. So I really appreciate that.
The one exception to that is actually like the empty. If the lattice of central idempotence has a bottom element 0, then you also have to think about C restrict 0. That's not literally equal to the terminal category, because the way we define it, it has the same objects as C itself. So that's the one level where there's an equivalence other than and not an isomorphism.
Okay, thank you. Yeah.
I have a related question. You said your representation theorem comprises other theorems, and you mentioned the one by Takahashi on Hilbert modules, which is kind of the analog of the Serre-Swan theorem for that you have already mentioned before. But I don't see really how this is. Is this a direct special case that I can deduce, say, the Serre-Swan theorem from this embedding theorem? And then, if yes, how does this work?
So the spirit theorem is very much like Serre-Swan in that it takes certain sections of a certain bundle. But Takahashi has to be more careful because he's talking about Hilbert modules and not just modules. So he takes sections that vanish at infinity. So it's not literally Serre-Swan. Sorry, the question was something else, I think.
The question was, how is this theorem directly a special case of your representation theorem?
Yeah, so Takahashi says that Hilbert modules are the same thing as continuous field of Hilbert spaces. Other people have shown that that's the same thing. Simon Henry in Canada actually shown that that's the same thing as a Hilbert space in the category of sheaves, or in other words, a sheaf of Hilbert spaces. And I guess you combine the two things. So this is, I guess what he's using there is that a sheaf over X is the same as an étale bundle over X. There's this translation going on. So it's not literally an instant of that. That's right. You need to do this étale bundle translation.
I see. I have one more question, but do other people have more questions? So then maybe I ask that. It's a more general question, but I'm not a category theorist, so I would like to know how you guys think about this. So, for example, you did an awful lot of construction with categories. At one point, you took the co-limit and stuff like this. I would, from my background, think that there is set theoretical difficulty in doing this. So and all these things are not sets, and the axioms don't justify this. How do you think about this?
Yeah, that's the kind of thing I try to repress and not think about. So in the representation theorem, we ask that the thing you start with is small. That's one way of avoiding it, which means that when you take this co-limit of categories in the category of monodal categories, all of the things themselves are small. So that way you prevent all the size issues. I think you can maybe say something about more general classes of sets or collections. But the other thing you'll have to deal with, if you start with a big monoidal category, C, you look at a central idempotence, that might no longer be a set, right? So when we talk about where did it go? Not here, like this base space, capital X, that's then no longer going to be a set. And I guess you need to talk about growth and leak topologies or something on a big category. And like you, I like to stay away from that sort of nonsense. Small sets are fine for me.
I see. Okay. So this universe idea is not something that we try to use to make something. Is this sufficient as a background?
I don't know. I know it exists, this idea. I roughly know what it means, but I've never tried to use it.
Okay. All right. Further questions? Are there further questions? So if my question, I can't, let's see, I will try to read it in the chat. I will read it aloud. Hi, Chris. Sorry if my question is a little bit away from what you are presenting. May I know what the differences between categorical quantum mechanics and the Topos approach to quantum theory is, I think, because categorical quantum mechanics use symmetric monoidal dagger categories, while in the Topos approach, you use a pre-sheaf. Is there any connection between these two structures?
I can talk to you about that, but I think maybe this is not the right place to do it. So can I suggest that you send me an email and I'll try and answer that? Is that all right?
I'm only reading the questions, so Akko has to answer this.
Yeah, I think this is being recorded, so I don't want to ask you to put your email in the chat or something.
Okay, all right, here we go. So that answers for the time being. Or you will promise to answer it later. More questions?
I promise to answer later, yes.
More questions? If that is not the case, I would like to thank Chris again very, very, very much for taking all the effort to give these wonderful lectures here. It was absolutely great. Thank you very, very much for all the effort that you have put into this. And you had, I didn't like the remote idea at the beginning, to be honest, but I think it turned out to be very successful because we had participants from all over the globe, so to speak. So, and this is easier in this virtual format kind of. So I think it was a great success, and everybody could participate really easily. And you didn't have to travel here, right? Which is your semester still ongoing?
It is, yeah.
Yeah, here too. All right. Okay, so then I say bye-bye to everybody. Yeah, stop the recording and see you guys some other time, hopefully soon under other conditions. Yeah, all right. Bye-bye.
Thank you.